Okay, let's start. So, welcome everyone. My name is Vadym. I'm working at AWS, and today we're going to talk about connection storms. So imagine this picture. It's 2 a.m. in the morning, you're sleeping in your bed, suddenly, boom, pager goes off. Half asleep, you're grabbing your laptop, you're trying to make sense of what's going on. You open the Grafana with Valkey dashboard, but what do you see? You see that half of the metrics actually missing. There's a gaps. So what is it? It's like an exporter issue. What's going on? While you're trying to understand all this, actually the application team contacts you and say, oh, we can't connect to Valkey. After some investigation, few hours later, not few hours, like an hour later, you understand the root cause was a connection storm. So what is a connection storm? Let's talk about it. A connection storm is a sudden surge of TCP connections that overloads the network. In many cases, it happens in the networking layer, so basically even before Valkey can handle. And you know that Valkey is basically single-threaded, and it's not very hard to overload it. And this usually happens during application upgrades. For example, the application team rolls out a new version and all the clients start to connect at the same time. It can be because you decided to update Valkey to a newer version or patch something. Or even because you have some disruption in the network and after the disruption is over, everything back to normal, all the clients try to connect at the same time, boom, connection storm. So on the surface, we see that clients can't connect and we say, okay, connection storm, the network is overloaded. But let's talk a little bit deeper. What does it mean? What does it mean the network is overloaded? We will talk about the accept queue, sync queue, and contract table, and we will see how it affects the system. But before we go there, let's talk about the clients, because in the end, the root cause of connection storms are the clients. Yes, they try to connect, and this is what happens. So if you want to avoid the connection storms, your client has to do two things right. The first one is connection management. We can say that there are two main approaches to connection management. The first one is connection pool. It's, for example, it's used in many clients, but the one example that I think of is Valkey Pi. I think the contributor, maintainer of Valkey Pi is here, and he would happily answer the question about it. Yeah, so basically what connection pool does is it lets the client reuse the connection. So instead of opening a new connection each time the application needs a connection to Valkey, it reuses. It allows you to open multiple sockets and reuse them. Great, usually helps, but you need to remember to cap the maximum number of connections, because otherwise it kind of doesn't make sense. The second approach is multiplexing, is used, for example, by Glide. Glide, I'll say a few words. It's a relatively new client that is focused for enterprise. And if you have questions about this client, we have today we have Asaf. He would happily answer any questions about Glide. So what is multiplexing? So instead of keeping several connections, several sockets, we have one connection, one socket, and we multiplex multiple commands from multiple clients over this single connection. And it's great because instead of n connections, we have only one connection, lower overhead, few memory, etc. But of course has its drawbacks. For example, if you really need few TCP flows, it's kind of a bottleneck. The second thing is reconnection strategy. Reconnection strategy, I think, was mentioned today during the LDAP talk. It's basically how client behaves when it fails to connect. And the recommended approach here is to use exponential backoff with a jitter. In this strategy, we have 4 main elements. The first one is a factor, basically the base timeout of a connection attempt. We also have the exponent base. This component controls how the timeout grows with each failure attempt. Of course, we have the number of retries. For example, if application wants to give up after some amount of failures and propagate there to the stack. And the interesting part is the jitter. Jitter is like a randomness component. It allows us to use, instead of fixed timeout, it allows us to use a random, some randomness around it. So for example, instead of waiting for, I don't know, 2 seconds, we wait a little bit more or a little bit less, depending on the random. And it's very, very helpful because we don't want all our clients to synchronously connect, try to reconnect. Because if it happens, if we have really big number of clients, like a fleet of clients trying to connect at the same time, then even if they do the exponential backoff, they do this synchronously, and every time they will try together, and together they will fail. So jitter will help in this situation. On the left, you can see the algorithm, how it works. So we try, if we succeed, we succeed. If no, we increase the time, and this is the loop. So most clients give you, it's like many clients use this strategy by default because it's very, very good in the field. It showed itself very good in the field. And if you don't happy with the defaults, you of course can tweak it. Here I put example in Glide, in Python, how to configure the backoff strategy and use it in a connection. Now let's talk about, it was the client side. Now let's go to the server side. So there are cases when you can't control the clients and you only control the servers. So what the first thing that you want, you don't want to do a lot of investigation before you understand there is a connection storm, like was in the original story, because you want to look at your dashboard and to understand the problem right away. So in the original horror story that I tried to tell at the beginning, what actually was missing. So what people usually put on the Valkey related dashboards, related to network, of course. So there are number of connected clients, number of connection, total number of connection, active number of connections, number of connections that Valkey rejected, etc. But as I said, it doesn't tell the full picture. What is usually missing is the kernel level metrics like size of the queues, size of contract table, and in case you deploy into cloud environment, there are some cloud-related metrics that you also need to be aware of because they are there. So let's talk about each of them a little bit with a little bit details. So first one is the contract table. What is it? It's a special data structure in Linux kernel that tracks all the active network connection. It's not used always, but if you have special firewall rules, if you have NAT, etc., it is there. If you deploy to Kubernetes in 5 minutes. I have 5 minutes? Yes. Okay. So if you deploy into Kubernetes, you have it. If you in the cloud, you have it. And the size is limited, right? So when this table overflows, your new connection just get dropped. There's a metric by kernel that you can observe. You of course can configure the size. And now let's talk about TCP connection. Here you can see the illustration to the classic three-way handshake. So client sends the SYN. This is the start initiation of the connection. Server receives it and put in a SYN queue. What is SYN queue? another data structure that you use in kernel, and it keeps the half-open TCP connections. And of course, it has a limited size, and when it overflows, the new connection can be dropped, or there's something that's called sync cookies. We won't talk about it too much, but it's a way for kernel not to add new entries and keep the handshake active. And there's no metric for this, but you can use socket stat utility to monitor the size. After a server put the entry into the sync queue, it responds with synack. Clients receives it and finish the connection with ACK. At this point, kernel puts the connection into the accept queue, and it's another useful data structure that tracks all the connections that finish the TCP handshake, and they're waiting for process to accept them. So in our case, this is where the connection stays until Valkey calls the accept in the main loop. And when this actually full, for example, Valkey too slow to accept the connections, kernel just reset the connection. Again, use socket stats to observe the current size. And the configuration. This one is more trickier because it has two configurations. The one comes from the kernel, the somaxcon, and the other one is on the process level. In our case, Valkey. In Valkey, we have this TCP backlog size that also controls the size of accept queue, and the lesser of them will be the actual size of the accept queue. So make sure you tweak both of them if you need. Now, I mentioned the cloud. So if you use cloud, for example, AWS or another provider, and it doesn't matter. You deploy on virtual machine directly, or you use Kubernetes, or use managed services. In any case, in 99% that you have one of these limits, or all of them. So usually there are limits on the bandwidth, a limit on the contract, additional to the contract table that we talked about before, and a limit on the packets per second. When you exceed these limits, your packets start to go to the queue, and if it's not enough to slow you down, your packets will be dropped. So to summarize, if you want to survive the connection storm, 4 things to remember. First of all, make clients to manage connections. Use connection pools or multiplexing. Second, use backoff strategies, backoff with exponential backoff with a jitter. Third thing, observe kernel metrics. Observing Valkey metrics is very useful, important, but in some cases not enough. So remember, do it. And the last thing, remember, if you deploy in cloud and not on premises, remember that cloud providers put additional limits on the network, and you should be aware of it and monitor it. Thank you very much.